Hey everyone, and welcome to lesson 5.10, and this is on area of a segment of a circle. And a segment we can see is kind of highlighted in the diagram below. So the segment is just this shaded region here. And we have all the skills kind of needed at this point to find the area of that shape. So if I just kind of provide some quick values on this diagram, I might say that, maybe we say that this is 60 degrees here. And if I give this a radius of 8, that is actually all that we're going to need in order to figure out the area of that shaded region. And the first thing that we kind of need to realize here is that the area of a segment, which is, just this shaded region here, can be thought of as being equal to the area of a sector, right? So we learned how to figure out the area of a sector yesterday, minus just the area of this triangle. So if I manage to basically figure out the area of the sector, figure out the area of that triangle, then I should be all set from there. And in this diagram, figuring out the area of the sector shouldn't be all that bad. So if I have my sector area, what I learned yesterday, apologies, is that I can take the area of the circle, so the entire thing, so that would be pi times 8 squared, pi r squared, and then I multiply it by basically the proportion of the circle that I want, or the subset that I'm actually looking for. So that would be 60 over 360. So that's the area of this entire shaded in region here. Okay, so that includes my shaded region. And now I'm going to look to figure out how I can take away the area of the triangle, because then I'll have what I need. And just for kind of our purposes, I'm going to get a 3 decimal approximation out of this. So I'm looking at, let's do that, doing 64 pi divided by 6 is actually equivalent to what I have there. So the area of that sector is 33.510. So I'll just leave it at that. All right, so now I need to figure out the area of this triangle. And that can be somewhat difficult if I don't actually adjust my thinking on this or look at this triangle somewhat differently. So what I'm going to do is actually, I've got that 60 degrees in the middle. But what I plan on doing is drawing basically the altitude or the height of this triangle. Okay, and I can do that by splitting that angle directly in half. And this is kind of an important property of a circle, where if I take a chord, which is that line that connects 2 points on my circle, any basically radius or diameter is going to be perfectly perpendicular to that. So I end up, when I do that, actually creating 2 triangles that are 2 30, 60, 90 triangles. And if I can figure out basically the base and the height of that triangle, then obviously kind of I should be all set to go. So this would be my base and this would be my height that I'm looking for. If I take this triangle just off to the side here so that I can look at it in a little bit more detail, I've got 30 degrees, 60 degrees, 8. And then I've got, I could do this with special right triangles in this particular case, but that's a little bit limited at times. So instead, what I would probably do is use trig in order to get these values. So the height of this triangle, this particular side, if I use cosine here, I could say that the cosine of 30 degrees is adjacent over hypotenuse. So that would be h over 8. And then if I just want a value for h, I can say 8 times the cosine of 30 is my height. So this is 8 times the cosine of 30. And then the base of this triangle, if I just use sine, I can end up basically figuring out the same thing. So I'm even just going to kind of jump to that and say that the base here is going to be 8 times the sine of 30. So this is now 8 times the sine of 30. What's nice is because I have two of these triangles, I don't, normally area of a triangle would be 1/2 times base times height. But because I have two identical triangles, I can really kind of consider that the area of two of those triangles is just going to be base times height because they're identical. So here I had my sector area. Now I'm going to calculate my triangle area, which is just going to be 8 sine 30 times 8 cosine 30. That's going to give me this entire shaded region here, which I'm going to take away from my sector area, and then I'll have my segment area. So if I go to get a 3 decimal approximation for this, so that's 64 sine 30 cosine 30. I am looking at 27.712. And then as we kind of said in the beginning, if I just subtract the two of those from one another, 33.51 minus my answer. And that's, more than what we need. So here we would end up with an area of 5.79. Tough to, again, kind of gauge the reasonableness of this. I guess it doesn't seem outrageous to me at this point. You could approximate it, I guess, if we want to consider like, oh, well, if the radius is 8, then this entire shaded region would be an area of 64, and then just kind of eyeball it from there. But again, good to just have some skills in the back of your head for figuring out if that's reasonable or not. So then we have this area of a general segment. So this, was specific to the example that we had above. But if all I had was a radius and a theta, is there an equation that I can kind of simplify down to if I needed? And, the basic premise isn't going to change. We're still going to do sector minus triangle. But we're going to take a look at kind of where some pieces came in and replace them. Instead of replacing them with 8 and with 30, we're going to leave them as our radius and theta here. So the sector was pi times my radius squared times, here that angle kind of came into play. So this was theta over 360. And that's just our area of a sector equation. So even if I don't have a diagram, I can still just, somebody tells me the radius and theta, I can figure out the area of that sector. And then for my triangle, if I'm looking at, what this ended up looking like here, I have that 8 sine 30 times 8 cosine 30. These 8s are my radius, and those will eventually get multiplied together, so I could even shortcut that to just r squared, and then I'm going to have sine theta cosine theta. That is pretty close to as simplified as I would expect to have it. So if we need to figure out the area of a segment, all we need to be given is the radius and theta, and we can plug it into this equation here. It's probably encouraged for maybe this first one, there's only 3 examples today just because, um, I don't need to hit you over the head a bunch of times with this information. But here, maybe just drawing out that first one so that we can continue to make sense of what we're doing. So I have this that I'm kind of extracting. This first line is going to come down, and that 120 degrees, oh, actually that's a good thing I did this because that's going to adjust something in our equation. These end up being 30. So yeah, what I just noticed was that angle that we're probably going to be given in our diagram is actually twice the angle that we want put into our equations. So in this like general equation here, what I would actually want is that initial angle divided by 2. Okay, right? Because we started actually with 60 on this diagram, and then I had to split it into 30, and that's what I used all throughout those equations. Although this one, we still used 64, so I'm going to leave this as just theta. Okay. So I'm going to just use my equation here that I have. This was 24. So my area for this should be pi times 24 squared times 120 over 360. Again, for that one, we used just the initial theta that we were given. Now I have r squared, and then a sine of theta divided by 2. So that would be sine of 60 cosine 60. And we can figure out what that is, plug it all into our calculator, but again, that's basically as accurate as we would need, or as we kind of should be getting to. All right, so see if we can just do these other two. Again, drawing the little side diagrams is probably going to be helpful for us, but yeah, don't need to kind of push us too hard today. All right, thanks.